Okay, we worked some problems last time, and I think I had put those a little too soon. So we need to discuss regioselectivity and stereoselectivity here. So from an E1 reaction, we can get elimination products and a substitution product, and it turns out we can get Hofmann or Zaitsev elimination, okay, and we can get substitution. Okay, so there's more than one regioisomer possible for some substrates, but E1 reactions are always going to give the most stable alkene because they're just using a weak base, and so we can't use like a big bulky base here to get that Hofmann product that we want. So E1 reactions are regioselective, but we can't control that like we do E2 reactions. Okay, it's possible to obtain several stereoisomers as well. So we get regioisomers and then we get stereoisomers, such as this. Okay, so we could eliminate and get the Hofmann product like we have here. So remember, our carbocation is going to end up here. Or we could get the E and Z isomers, such as here and here, right? Or cis and trans, if that were the case. Okay, so we have to worry about regioselectivity and stereoselectivity, and then we have the substitution products from SN1 being a possibility as well. So for these E1 and SN1 reactions, you can see that we get a pile of crap, okay, and they're just not synthetically useful. But you have to keep that in mind, that if you're going to store these, or you're going to run a reaction in something like this, then these are going to be possibilities, okay? So the E1 reaction is going to give the most stable alkene when two stereoisomers are possible, okay? And, you know, the regiochemistry is important. If that's important, then you're going to get preferentially Zaitsev, preferentially trans versus cis. But all of these products are possible and still obtained, so we just get really a pile of crap. So as far as the SN1, we didn't talk about that yet. We can get enantiomers formed because we go through this carbocation, which has a planar transition state. So when the leaving group picks up and leaves, we form this planar carbocation. Now the nucleophile can add from either side. So if it adds from, say, the right side, then we're going to get this product. But if the nucleophile adds from, say, the left side, then we're going to get this product. Okay, so if it adds from the right, we get what's called retention of configuration, and if it adds from the left, we get what's called inversion of configuration. Okay, so we can either get retention or inversion depending on which side the nucleophile adds from, and generally it's going to add about 50-50 from either side. So we get a 50-50 mixture of inversion and retention of configuration. We don't get backside attack like we did with SN2. And this 50-50 mixture is called a racemic mixture. It's about 50% one and 50% the other. So if you go through a carbocation intermediate, you're losing any stereochemistry that you had in your starting material. Okay? But in fact, it's not quite exactly 50-50. You don't get exactly a racemic mixture because of what's called closely associated ion pairing. When that leaving group picks up and leaves, it's going to be still hanging around, and it's going to tend to hang around from the side that it left from, blocking that side just a little bit from attack. So your inversion product is going to be slightly higher than 50%, and your retention product is going to be slightly lower than 50%. But for your purposes, you can just consider this to lead to a 50-50 mixture of inversion and retention products. So essentially you get a racemic mixture when doing this reaction. Okay, so in the next topic we'll talk about kinetic isotope effects.